You are currently taking a virtual trip down a borehole from the western coalfield of the Sydney Basin, courtesy of the logs produced by an acoustic televiewer. The televiewer tool transmits ultrasound pulses into the borehole wall and records both the time taken for the signal to return and the amplitude of the returning signal. The image we're looking at now is a composite of both those parameters. The colour variability is due to changes in the amplitude, with the darker colours indicating softer or more fractured strata, while the varying shape of the borehole is due to differences in travel time of the signal. So the jagged blue zones shown in the video are places where the borehole wall has been fractured and enlarged due to high horizontal stresses. This process is called borehole breakout, and we'll look at that aspect later in the presentation. It's now become common practice in the coal industry to include the acoustic televiewer as one of the tools routinely used in exploration programs. Unfortunately, it seems that the resulting logs are only rarely being utilised. One reason for this is that specialised software is needed for the analysis. So companies either need to make an expensive outlay or pay consultants to do the analysis for them. Another reason for the lack of usage may be that as yet there isn't a widespread understanding of just how useful these logs can be. Whatever the reason, the fact remains that many companies are failing to make the most of a valuable resource that they have in their keeping. Let's look at what kinds of information you should be gathering from your televiewer logs. Numbers 2 and 3 on this list are reasonably well-known uses, and we'll look at those a little later. But the first one, making your logging more accurate, appears to be largely ignored in the industry. This is a wasted opportunity because the televiewer amplitude log can provide great insights into the nature of the intersected strata. The amplitude log can improve the accuracy of geological logging because it can provide an almost photographic quality image of the strata. This is especially the case when the hole has been cored, because the smoother the wall of the hole, the cleaner the image will be. Now you might think that if you have the core, why would you need to refer to the image? There are two good answers to that question. Firstly, the image shows the complete picture. So if the core is badly broken and/or it is suspected of including core loss, the image can be used to help reconstruct an accurate stratigraphic record of what is really there. Secondly, the amplitude image of a coal seam can reveal details that go way beyond what you can see with just your eyesight alone. So this means that even the least experienced geologist should be able to produce a reliable log if they have a televiewer image to refer to. Here's an example of the level of detail that an amplitude log can show. Individual conglomerate pebbles can clearly be seen in this image due to their high amplitude response, which contrasts with the weaker response of the softer matrix and cement. Note that the pebbles aren't really as elongated as they appear to be here. This is caused by the televiewer log being displayed as a rolled out 2D image of the entire borehole wall. But in terms of increasing the accuracy of geological logging, the amplitude log really shines when it comes to coal seams. Here is a 1:20 view of the basal part of a Great Northern Seam intersection. The figure also includes some common geophysical logs and a raw ash profile. Let's look at some of the fine detail that can be seen. Very thin stone bands, such as the one at 179.4 metres, stand out clearly on the image, but show no indication on the density log. This could be invaluable when trying to find important stratigraphic markers, especially if those bands are carbonaceous and difficult to find visually. The large V-shaped feature, seen at about 181 metres, was noted in the geological log as being a possible fault. but the image shows that none of the stone or coal bands show any displacement, so the feature is simply a significant cleat. The amplitude image is sensitive enough to differentiate between coal lithotypes. For example, the brighter coal from 179.6 to 179.8 metres stands out from the lighter coloured, duller coal above and below. This could be useful when determining appropriate sample boundaries and also for fine-tuning the lithological log. As an example of this, towards the base of the seam, the section from 181.6 to 181.95 metres has been logged as dull minor banded and dull banded. But looking at the relative lightness of the image, this might be an overly generous interpretation. The raw rash of 33% confirms this view. Similarly, it looks like the carved mudstone shown on the lith log at the base of the seam is actually coalier over its upper half than it has been logged. So in effect, the seam thickness should be slightly greater. Here's another example, this time of the Fassifern seam. Again, the correlation between relative lightness of the amplitude image and raw ash can clearly be seen, especially towards the base of the coal seam. In this case, the geologist has been slightly generous in samples 27 and 29 by logging some high ash material as dull minor banded. But to be fair, it is very difficult to be consistently accurate when logging dull shaly coal and coaly shale. This tool can make the job much easier, so let's use it. My suggestion would be that the initial lith log be quickly imported into a program such as WellCAD, along with the televiewer, caliper, gamma and density logs. If this is done at an early stage, any issues with core loss, missed marker bands or mislogged high ash material can be sorted out before any important decisions need to be made. This could help to avoid some awkward issues that might arise later when an incorrectly logged borehole doesn't quite fit in with surrounding holes. Now let's turn our attention to structural uses of the televiewer logs. First up, we'll look at the process of measuring the orientation of geological structures like joints, cleats and bedding planes. Fractures stand out prominently on the amplitude image because the broken material, or open space if present, absorbs more acoustic energy than the solid unbroken strata. This makes the trace of a fracture appear as a dark sinusoidal curve on the image. Bedding planes are made apparent by the different amplitude responses of different rock types. The example we're looking at here is a section of jointed Awabba tuff from the Hunter coalfield, and the diagram below the photos is a WellCAD plot of the same section of strata. Structure picking is done by clicking at several places on the joint trace shown on the amplitude image. The software then attempts to draw a curve of best fit, with this theoretical curve then overlying the image. A second copy of the amplitude log has been included here so that I could clearly show what televiewer evidence was used to create each theoretical joint. Most of the joints shown here are very good examples because the complete sinusoidal curve is shown on the log. Often this is not the case, and you may only have a limited view of part of the curve. This makes it hard to be sure that you've accurately picked the true trace of the joint. The lowest joint shown on the diagram is an example of this issue. So structure picking can be subjective, and you have to use discretion as to whether you have good enough data to risk including some structures. Each picked structure can be allocated to a user-defined category, and I assign those that are considered a bit risky to a separate category. The joints that are coloured green in this diagram are examples of that process. And this colour coding is carried across into the interpretive logs as well, so it can be readily seen whether the high risk picks are falsely skewing the data. And this may well be the case here, with the lowermost risky joint being the green dot in the polar plot that lies to the south of the main cluster of poles. Once the structural features have been picked, the software can then display the data in a number of different ways. In this diagram, I've created a 3D view of the amplitude log, which enables the joint planes to be displayed as they occur naturally. The next log is a tadpole diagram, which shows each structure in terms of its dip and dip direction, with the position of the head indicating the dip from 0 degrees on the left to 90 degrees on the right, and the tail indicates the azimuth of the dip direction. As can be seen here, the dominant dip direction is to the northeast. On the far right of the diagram is a column which allows polar plots to be drawn for any given section of the strata. This of course allows dominant structural trends to be easily identified. The final televiewer usage that I'd like to cover is the determination of the major horizontal stress direction. This is achieved by using the televiewer logs to identify and measure the orientation of borehole breakout. Borehole breakout is the stress-induced enlargement of a borehole, and it occurs when the stresses around the borehole are greater than what is required to cause compressive failure of the wall material. As shown here, the breakout normally develops at two opposing sides of the borehole, which are perpendicular to the major stress direction. This section of strata is from the same borehole that was featured in the opening video, and the following slide shows how this particular breakout interval can be analysed in WorldCAD to determine stress direction. Both the travel time and amplitude logs clearly show the breakout. It appears as two parallel strips on the rolled out 2D versions of each log. The darker colour on the travel time log indicates that the signal has had a longer journey where the borehole has been widened due to breakout. And the darker colour on the amplitude log is a result of the borehole wall being rough and variable where breakout has occurred. The breakouts are manually picked on the amplitude log, and the results can then be displayed in a number of ways in WorldCAD. The breakout azimuth column shows the picks displayed in the form of a rose diagram. This particular pick has an azimuth that is roughly north-south, which means that the maximum stress direction is oriented east-west. A cross-section log is also shown. This is based on data from the travel time log and shows the average borehole cross-sectional shape over the selected depth range. This is used to verify that the breakout zone in question displays distinctive bidirectional bulging. By way of contrast, another cross-section has been drawn in an area that shows no indication of breakout, and as can be seen, the cross-section there is perfectly circular. There you have some of the benefits that can be gained by fully utilising your Acoustic Televiewer logs. The additional financial cost of doing this is relatively minor compared to the overall costs involved in an exploration program. So the question is, can you afford not to make the most of this valuable resource?